that.
Okay, so good morning. My topic is transposition cipher. So today I'm going to talk about the Railford cipher, root cipher, the columnar transposition cipher, and the Minkowski transposition cipher. Just an introduction to transposition ciphers. Transposition ciphers are a bit different than substitution ciphers. So in substitution ciphers, what we do is we basically replace each letter with a different letter to produce the ciphertext. So in transposition cipher, the letters are just jumbled or just moved around to produce the ciphertext. So the first example here is just reversing the order of the letters in the plain text. So here the plain text is say snowflower. So the ciphertext is this thing revolve, like WONS. So here the order of the letters is also reversed and the words are also reversed. The second example is reversing the letters of each word, but not the order in which the words are written. So again, the plain text is snowflower and the ciphertext here is this thing. So here the order of the words is not reversed, just the letters are jumbled around. Another type of transposition cipher is Cytail, which was an encryption device that was used by the ancient Greeks and Spartans. So the system just consisted of a polygonal rod or cylinder, and around it was wrapped a piece of parchment. So the sender would generally write the message along the faces of the rod. So as seen here, so the message was send more troops to southern flank, as we can see here. So if I just remove this ribbon from this polygonal rod, I'll read this messages ST, SF, and so on, like EROL. So this will be a message that will make no sense to us. So in order to decrypt this message, we need to wrap this piece of ribbon around the polygonal rod of same shape or size that was used by the sender to encrypt this message. So this was the Cytail, and it was one of the first uses of tools in cryptography.
Yeah, but is it everyone clear? Any questions to ask?
No, sir.
Yes, it is clear. Okay. Yeah, thanks.
Okay, so the first one is Railford cipher. So the Railford cipher is an easy to apply transposition cipher that jumbles up the order of the letters of a message in a quick and a convenient way. So for the encryption of the Railford cipher, we need a plain text, and along with the plain text, we need a key. So here the key is basically a number which will tell us how many rows we need to construct the grid. So we draw the grid with the given number of rows, and the number of columns is the number of letters in the plain text. So let us consider the example where the plain text is snowflower blossoms with the key of 3. So when the key is 3, that means that the number of rows to construct the grid is 3. And here the number of letters in the plain text is 18. So there are 18 columns, and we might add new columns in order to just complete the zigzag pattern. So here in Railford cipher, what we do is we start from the top left box in the grid, and we start inserting letters from the plain text in a zigzag pattern. So we go down diagonally, and we then just bounce back up to the first row. So in this way, we just go on inserting the letters in the plain text. And once I'm done, like the snowflower blossoms is the last letter in the plain text, I have not completed the zigzag pattern, so I'll just insert an X here. So it is called as a null or a placeholder. It is just inserted to complete this pattern. Now that I've constructed this grid, I'll encrypt this message like by reading the rows of the grid. So here I'll read this message row wise. So it will be S, F, E, O, M. Then I'm done with the first row. Then I'll come to the second row and N, W, L, W, so on up till the last letter. So this is how we encrypt in the rail-fence cipher. For decryption, we need to know the key that was used for encryption and the ciphertext. So after knowing the key, we can construct the grid. So there will be 3 rows here, and the number of columns will be the number of letters in the plain text. So here the number of letters are 19. So the grid will have 3 rows and 19 columns. So for decryption, we start again with the top left box in the grid, and we start inserting the first letter. Then we'll go on inserting a dash until we bounce back to the first row. Once we are back to the first row, we'll insert the next letter and so on. So when I reach this M, if I go down diagonally, there is no grid here. So I'll have to come back to the second row. So in this way, we decrypt the message in rail-fence cipher. So this is what we get. We get the plain text, snowflower blossoms. So after this, there is an X. So this is just a null or a placeholder. So it is an easy transposition cipher, and it is not secure as we have limited usable keys, especially for short messages. So here the length of the message needs to be twice the length of the key, or more preferably it should be 3 times the length of the key, because there should be enough space for movement of letters. Also, the use of nulls that we use here, it can have an effect on the security of the cipher, because for an individual who is trying to gain access to the confidential message, he might know that there is an end of the line here. So he can have a sensible guess at what the key was used to encrypt this message. So instead of just using X, we can use the most common letter that appears in English language, that is E. Because when I encrypt this message and I'm sending it to some person, he might know that this is the plain text, this is the message that I want to send, and the E's will appear at the end of the message. So he'll get to know that they make no sense in the message. So that's about the rail-fence cipher.
Yeah, so any questions? How to decrypt?
Should I explain again?
No, I'm so is it everyone clear that how to decrypt?
Yes, sir.
Okay, right. Okay, then you can go.
Okay. So another way to make encryption a little bit more secure is to keep the spaces as characters and include them in the encryption table. So the plain text was this, and there were spaces after each word. So after snow, there is this box which is empty. So here we are we are considering these spaces just like every other letter. So flower, and then there is a space, then blossoms, and then there is a placeholder to just complete the grid. And again, the ciphertext we'll read row wise. So S, then there is a space here, then W, B, S, X, till so on, E, and after E there is a space here, and so on. So this is the ciphertext when we want to include the spaces as characters in the encryption table. Next is the root cipher. So root cipher is a transposition cipher where the key is which route we have to follow when reading the ciphertext from the block that we create using the plain text. So the plain text is written in a grid row-wise, and then we read off the following according to the route that is given. So for root cipher, the example is, say, the plain text is abort the mission, you have been spotted. And for the encryption, we need to know the plain text and we need to know the route. So the route here is spiraling inwards counterclockwise from the bottom right. This is the route which is given. And we need to either decide the number of columns or the number of rows in order to construct the grid. So here, the number of columns I've taken as 5. So now I'll write this plain text So number of columns is 5. Then the number of rows will be the length of this message along with the placeholders divided by 5. So there will be 7 rows that are constructed in this grid. So we'll write the plain text row wise, and again 2 placeholders just to construct a grid of reasonable size. And then we'll, for getting the cipher text, we'll read this message following the route. So the route here is spiraling inwards from counterclockwise from the bottom right. So we start from the bottom right and we spiral inwards. So this is the route that we follow. So here the cipher text is this XTEAN, then ITORB, and so on. So here the cipher text is just divided into the blocks of length 5. So it has nothing to do with the spaces in the plain text, because here we are just dividing it to just avoid any errors or make the text easily readable. So for the decryption of the root cipher, we need to know the route that was used and the width or height of the grid. So we then construct the grid of appropriate size and write the cipher text in it following the route given. And then we read off these rows to get the plain text that was encrypted. So here the cipher text was this thing, and the route used was spiraling inwards counterclockwise from the bottom right. The number of columns was 5. So again, to get the number of rows, we'll just divide the length of the cipher text by 5. So there were 7 rows. And then we start decrypting the message by inserting these letters following the route. So we start filling this like spiraling inwards. So after we fill every letter from the cipher text, we get the plain text that was decrypted, encrypted.
Yeah, actually, very good. Everything is clear. But if any other person has any doubts, is it everyone clear? Suresh?
Yes.
Yeah, please go ahead, Kanak. Yeah, please go ahead.
No, sir, I said yes, everything is clear.
Everything is clear. That's what actually she's explaining very neatly. Yeah, okay. Rutuja, go ahead.
So the root cipher is again very easy to use. Then it helps us to jumble up a message, like the letters in the message, very quickly. But it might have some problems depending on what route we are picking up. So here I could have selected the routes like reading this column wise, or just zigzagging up and down, or some other route like spiraling from this corner inside and so on. So I'll have to carefully select the route, because it might just leave, like when I'm encrypting the message, it might just leave out large chunks of plain text in the right order, or just simply reversed order. So that will give the idea of, it will give an hint of what route was used for the interceptor. So we need to carefully select the route. And for suitably like very lengthy messages, there are infinitely many routes that could be taken through the grid. So it is just limited only by imagination and ease of communication of the route. And one historical use of the root cipher was the Union root cipher that was used by the Union forces during the American Civil War. So that's it about the root cipher. So the next is columnar transposition cipher. So it is just a type of root cipher where the root is we are reading the column. So here the root was given. So in columnar transposition, we'll just read this column wise. So for the encryption, we first pick up a keyword, And then we write the plain text out in a grid where the number of columns will be the number of letters in the keyword that we are using. This keyword is not anyway related to the plain text. It could be any word in general. And then we just name the columns with the respective letter of the keyword and then number the columns alphabetically with respect to the keyword. And the root will be reading of the columns in order. So what we do is, for example, here I've taken the plain text. The tomato is a plant in the nightshade family. And the keyword is tomato. So the keyword is written on the top. And then we just assign a number to this letters alphabetically. So A appears first, so it is assigned a number 1, then M, so 2. Now in this keyword, O is appearing twice. So the rule is the letter which appears first in the keyword is assigned the number first. So here I'll assign, so O appears first in this keyword, so I'll assign a number 3 here, and then 4 to this O. Again, T appears twice, so we'll assign 5 to this T, which appears first in the keyword, and then to 6, or 6 to T, sorry. Then the plain text is written row-wise. So here the tomato is a plant in the nightshade family. And then there are 4 nulls that are used to just complete this grid. Now, to find the, cipher, to find the cipher text, we'll just read the columns which are numbered like accordingly, like from 1 to 2 and like in the ascending order. So here the first column is read first. So this is what we get for the first column, then the second column, then the third column, then the fourth column, fifth, and then sixth. So this is the ciphertext that we get. So this is the encryption process. For decrypting this ciphertext, so here I'm using the nulls for encryption. So there'll be, if I'm not using the nulls, then there'll be some different calculation to decrypt the message. So here nulls are used in encryption. So we first write the keyword and the alphabetical order of the letters of the keyword. Next, so here, this is the ciphertext that we got. The keyword, we need to note the keyword, which is tomato. And then in this example, now while decrypting, I know that the number of columns in this grid is the number of letters in the keyword. So here there are 7 letters in the keyword. So there will be 7 columns in the grid. Then to find the number of rows, I'll have to divide the length of the ciphertext by the length of the keyword. So the length of the ciphertext is 42 and length of the keyword is 6. So there'll be 7 rows in the grid. And we just construct this grid, write the keyword, then alphabetically assign a number to this keyword. And then for decryption process, we go on filling these letters in the columns which are numbered, like from 1, 2, 3, 4, 5, and 6. This is second, then this is the third, then fourth and fifth. So we get back the plain text that was encrypted. Is this clear?
Yes.
Okay. So if I said that if the nulls are not used in encryption, then we need to do a bit different calculation. So here I've just removed all the nulls that are used. So X, I've removed all the X that was used here for encrypting. So this is the ciphertext and the keyword remains the same. So if nulls are not used, again to get the number of columns, it will be the same as the number of letters in the keyword. And to get the number of rows, we'll have to divide the length of the ciphertext by the length of the keyword. So earlier, the length of the ciphertext was 42. If I remove all the nulls, so there were 4 nulls that were used. So 42 minus 4 will be 38. And then 38 divided by 6 is 6.33. So this is not a whole number. So we'll round it off to the next whole number. So the number of rows will be 7 and the number of columns is 6. Now, in order to find what number of boxes are there in the grid, we'll just multiply these 2 numbers, the number of rows and the number of columns. 7, 6 are so 42. And to find the number of nulls that would be used, we'll just subtract this 38, the length of the ciphertext, from this 42, which is the number of boxes in the grid. So we get 4. So if we were using nulls, then 4 nulls would have been used, as we saw in the earlier example. So we just black out these boxes so that we are not entering the letters in these boxes while just decrypting the message. So again, we start filling this letters in the ciphertext from the first row. So TINESA. Then we go to the second column, then EOAHTF, and then the third column, and so on. So here we get HTLTHE. So we go on filling until we reach the last column, and then we move on to the next column. So we see here that when we decrypt the message, we get back the plain text that was encrypted. And these boxes are not used because they're just blacked out. So the columnar transposition cipher, it basically has the security of the transposition cipher with the extra benefit of just utilizing a keyword. So it is basically easy to remember, like encrypting in this way rather than just remembering some complex root. And one of the key benefits of transposition cipher is that we can apply it more than once. So here, when I'm writing this message, keyword is this, we are writing the plain text row wise. Then we can get the ciphertext, like reading the columns which are numbered in an ascending order. Then I can again apply the columnar transposition. But in this case, what we do is this ciphertext is now entered row wise as plain text here. And again, we read the columns numbered in an ascending order to get the ciphertext. So it is called as a double transposition cipher, and it increases the security of the cipher significantly. So first time I'm using this keyword, the second time I can use the same keyword or some different keyword of different length. Are there any doubts here?
Ritisha, can you go back 2 slides? I wanted to see during decryption, how do we know the number of X's that we put at the end?
This time?
Yeah, this one, just one.
Just
Oh, okay. So here during decryption, you assume that nulls are not used. First point. Okay,
yes,
okay.
yes.
Okay. Thank you.
So just a minute.
Yeah, sure. Is it stuck? What happened?
Yes, sir, it got stuck.
You can do what? You can do unshare and share again. That only it becomes.
Yes, now. Okay.
Again share, it will work.
Okay, so in Minkowski transposition cipher, it is just a variant of columnar transposition. So in columnar transposition, what we did was, if there were the repeating letters in the keyword, so here in this keyword, there are 2 O's which are repeating. Then there are two T's that are repeating. So what we did was we assigned a number to the letter which was occurring first. So here we assigned a 3 to this O because it was appearing first in the keyword, and then 4 to this O. So in Minkowski, what we do is we assign the same number to these two keywords, to these two letters which are repeating in the keyword. So it is same as columnar transposition cipher, except for the case where the repeated letters, there are repeated letters in the keyword. Then the same thing. So we start constructing this grid. Number of columns is same as the number of letters in the keyword. Then here we assign first number 1 to the letter A, then 2 to M. There are two O's that are repeating. So we assign the same number, so 3 and 3. And there are two T's that are repeating. So we assign 4 to both of them. Then again, we start writing the plain text row-wise. And for encrypting this message, what we do is for the number which are appearing just once. So there is only one here, like there is no repetition of one. So we read this column. For 2 again, there is just a single 2. So we read this column. Now there are two threes. So we encrypt this like HM, like row wise, TA, LI, TI, and so on. And again for the fourth column, TO, AS, PT, up till we reach the last row. So this is the ciphertext that we get. Now to decrypt this ciphertext, the length is 7. So there are 7 columns. And then there are then we start filling the first block into the first column. Then there is just 1, 2 here. So the second block, EOAH, this is filled in the second column. And now there are 2 threes. So for decrypting, we again fill it row wise. So HM, H here and M here, then T here and A here, and so on, like L, I, T. Now that I'm done with this block, I'll move to the next block. So I, H, A, E, I, Y, X, and so on. So I get the plain text that was encrypted. Are there any doubts here?
You want me to explain one more time, or any one of you? Hope every one of you concentrating. Okay, yeah. Go ahead. Then.
So again, the Minkowski transposition cipher, it will have all the advantages and disadvantages same as the columnar transposition cipher, and it is slightly less susceptible to be broken using anagramming, since the pattern of transposition is not as repetitive. And it is also possible to perform this Minkowski transposition cipher more than once, just like we did for the columnar transposition cipher, using multiple iterations, which will make it more secure. And again, we can use keywords of different lengths for each iterations. The next is anagramming. So anagramming is basically the skill of unjumbling a bunch of letters to reveal the words that are hidden within them. So an example would be an anagram of thing is night. So the letters are just moved around. So transposition cipher is nothing but we are just jumbling the letters in the plain text. So the skill of anagramming is the key to cryptanalysis of intercepts that have been encrypted using a transposition cipher. So in transposition cipher, we know that whatever the plain text is, we are just rearranging the letters and just jumbling the letters here and there. So the length of the, if there are say 2 M's here, in the ciphertext as well, I'll get 2 M's. So transposition cipher is less susceptible to frequency analysis. And again, for anagramming, it is, I mean, there is no given rule of thumb to start us off. It is just a skill that we need to develop, and there is no process that we can just apply. So some people are just very good at spotting words that are hidden within different words. So one way to practice anagramming is to play Scrabble. So it is just finding words that are hidden within a 7-letter word. So that's it. These were my references that I used. The Crypto Corner website, the Geeks for Geeks, and from Wikipedia, the Transposition Cipher.
Right. Okay. So see, and the security, not only the confidentiality. So till now we are discussing whatever, for example, previous talk also related to confidentiality only, right? What is the confidentiality? This is with encryption algorithms, it's possible. Information kept secret from the but all but authorized parties. Okay, only Alice and Bob will know the text. No other person will know it. That is the main purpose of the cryptography, right? In the beginning, but now that is changed actually because of the lot of everything becoming digital. So and people actually predicted this in future it become bit digital, and also people are doing things okay from the very long time. Yeah. So one is that integrity. What is integrity? So this can be done with MAC. MAC means what? Message authentication codes that we will discuss. And other one is digital signatures. These are the two things. In confidentiality can do by any encryption scheme, but integrity, these encryption algorithms may not guarantee integrity. What is integrity? Message not being modified in transit. While message is transmitting, so somebody take up the ciphertext and they will put another ciphertext. That means the original message is changed. Is it clear? What is integrity means? Okay.
Yes.
Yeah. So but encryption algorithms will not guarantee that integrity. Okay. Now, but Macs and digital signatures will take care. Now I am telling you the power of the digital signatures. That is my goal today. Right. Next one is message authentication. What is message authentication? So the sender of the message is authentic, and alternative way is the data origin authentication. So where actually data originated, that we know there is no change in that. Yeah. So integrity. So data authentication will take care of integrity. Am I correct or not correct? This is much complex. Message authentication, because if this is not, this happened, then integrity also happened. Right? Are you clear?
Yes.
You do see the difference between these two? Yeah, actually it's clear. I hope everyone is clear. See, so somebody told that April 14th is a holiday, right? So, but if it is for your classmate, then you may not predict. Message is he created, then you may not predict, he or she. So that has to come from the VC or your HOD or something like that, right? So then how do you know whether it is actually came from HOD? Yeah, how do you know? So there is a mail or there is a notice board पे उनका signature के साथ होगा ना, then we'll say that actually it came from the HOD. So it is originated at that point. So in between nobody also automatically not tampered because signature is there. Similarly, MAC authentication, something is there. So these two will take care of authentication. The MAC itself contains authentication. It is up to that extent only. So when it is taking care of authentication, it also takes care of integrity. That's why MAC takes care of these two, right? The next one is the very important one. It is non-repudiation. This only digital signatures can do it. What is that I am saying? That sender later should not deny. That happens, right? Many times. Somebody will promise you, but later I said that I do not say that. Yeah. So, but how do you do that? So that is actually digital signatures will help. So this is much more complicated thing. Yeah. So sender you cannot deny. Then actual authentication also taken care, integrity also taken care. This is much more complex. So these are the 4 items, and we are very relevant in the present state, right? Present day, right? You are all clear with these 4. Yeah. Any questions to ask me? These are the 4 security services we need to have in future, right? And you know that attackers are 2 types: passive attackers, just they see the ciphertext, and active attackers. Active attackers again classified. You know that only ciphertext is known, and chosen ciphertext, chosen plain text, like that. You know those things I discussed earlier. Now coming to the digital signature. A signature scheme is a method of signing a message stored in a electronic form. That is a simple definition. Signing a message stored in a electronic form. Yeah. So with the conventional signature, signature is part of the physical document being signed, right? When you sign it, you see the signature at the end, right? Yeah. But in the digital signature, not attached physically to a message that is signed. So that algorithm is used must be somehow blind the signature to the message. Is it okay? Somehow blind the signature to message. Is it part is okay? I think Kanak is clear.
Yes, sir.
Yes, sir.
Yeah. Yeah. So now verification. So verification is that anyone can verify. That is the beauty of this. Anyone will verify, it is signed. That is a purpose also, right? The audience, whoever getting that one, so it is verified. Yeah. And it is verified, and it is only signed by that person and all that thing. And which one is used for verification for this scheme actually? So public key crypto system is used. Okay. So to digital signatures, how public key crypto system? It is not digital signatures. Digital signature business actually from the public key. Actually, Diffie-Hellman, when they wrote the paper, actually they started with this digital signatures. So public key, one of the beautiful application is the digital signatures. Yeah. So digital signature, signing algorithm, and verification algorithm. What actually digital signature contains? Signing algorithm and verification algorithm. These are our two algorithms, right? So then automatical algorithm will have input and output. So what is the signature algorithm will contain? So it K is also part of it, but once you fix K, then I'll take the message and it will give output. Output is a signature. Verification algorithm, what happens? I will send, this is what it is missing in the Ankita's lecture, right? Discussion. So message also will send actually. Okay. Message is already there in the encryption. So message is there and then signature is there. Now verification algorithm is a binary. So they will use another key. So please see that this is K and this K is not same. Okay. Yeah, but even though I wrote K, but this K and this K not same. These K's belong to some key space. Okay. Now only thing is that a true or false only. Is any doubt still now? So you understand the difference between physical signature and digital signature. And the second point is that so anyone can verify. That is a beauty here. Anyone can verify. See, some people in physical signature, it is not possible. Signature, you do not know somebody's, right? But here anyone can verify. Yeah. And another thing is that digital signature, 2 algorithms will be there: signing algorithm as well as verifying algorithm. So signing algorithm is that it takes a message as input and gives the signature as output. Verification algorithm takes message as well as signature and will give output true or false only. Yeah. I'll give a small break here, few seconds. Any questions you can ask me. Yeah. Okay. So signature scheme is a 5 tuple: P, A, K, S, and V, right? Is it okay, Suresh?
Yes, sir.
Yeah, PLE means what? Plain possible messages, plain texts. What is a finite set of signatures? All right. What is key? Key space. Finite set of possible keys. What is S? Signing algorithms. It is set of algorithms. V is verification algorithms. That is the digital signature scheme contains. Is it okay? Plain text, signatures, key space, signature algorithm, signing algorithms, verification algorithms. Okay. Now for each K belong to, there is a, so signing algorithm, how it look like for each, we'll take first K. It is actually a function of two variables, but once we fix K, then as sign of K belong to S, one algorithm it will be there. So corresponding verification algorithm, right? So so corresponding to this K, there is another key, but there is a pair. These two are linked. That is the main beauty. These two are linked, but it is not private key crypto system. These keys are linked, but these are not same keys. Huh? Okay, even though the K looks like same. Okay, so for each encryption algorithm, right? So signature of key is an algorithm which take how input plain text and gives the signature. Verification algorithm takes plain text as well as signature, and it will give true or false. Right? You understand? So the following equation is satisfied. Okay, so yeah. So the pair x comma y, where x belong to plain text, y belong to, is called a signed message. Entire this ordered pair is called a signed message. Is it clear? Any questions till now? Rutuja, are you clear?
Yes, sir.
Okay, good. So for each K belongs to K, the functions, sign function, signature function, verification function. Here K is private key, here K is a public key. That is a beautiful part. Signing algorithm is uses the private key in the public crypto system, and verification algorithm is public key. That's why this key is public, anyone can verify. These are polynomial time algorithms because these has to be done in a polynomial time. Yeah. Is it clear? Yes. So now, because verification has to be done in polynomial time, we are verifying in very long time, that is no use of digital signature. Similarly, private key. So signing algorithm has to be done in polynomial time. Yeah. So these are two algorithms are polynomial time algorithms. Yeah. So this is again comes into the complexity theory, as Kanak told in the previous class, right? Yeah. So given a message X, it should be computationally infeasible for anyone other than allies to compute the signature Y. Okay, such that verification is this. Given a message X, it is computationally infeasible for any other person other than allies to compute the signature Y. Okay, I cannot get the same Y. Okay, so that this verification algorithm is true. See, it is a binary, though, but even then it is very difficult. We can use different Y also, another signature, another Y, but still it is true. That is computationally infeasible. These are the main ingredients required. Yeah. The signature scheme cannot be unconditionally secure, since Eve can test all possible signatures, right? Unconditionally secure means it is very, very difficult, right? But here my A is finite set, so Eve can test all possible signatures. I belong to A. Yeah. So digital signatures. What are the few applications? Now digital certificates are coming, secure e-commerce is going by digital signatures, legal signing and legal signing of contracts, right? You sign it, and so somebody want to purchase a land or something, right? So later non-repudiation is very important. Later he took the money, and later they say that you not paid the money. Are you following? This is very important, right? So digital signature become more famous, then court cases will be reduced. Do you agree? Hello?
Yes, sir.
Yeah, of course. These more cunning people will be there. So they are more powerful. They do other type of things. So, okay, provided if all these are nicely we create. Yeah. Okay. Now coming to the actual business now. Till now, this is the thing. So now coming to the how it goes actually. So general procedure, Alice and Bob. For example, Bob want to send a message, signed message, right? X is the message, S is the signature. So signing algorithm will be there. So KPR means what? Key, private key. K, private, public, private key. Private key is inputted to signature and message is inputted to signature. So signing algorithm, signing algorithm. Then I'll get the signature, right? So now Bob, what he will do, he will send both message as well as signature, both X comma S to Alice. Now Alice received both X. What is X message? What is a signature? Then what Alice will know now? What is advantage of this? In the original encryption schemes, only she will Alice receive only X. Now uske saath S bhi mil gaya. So then what is advantages, right? Will advantage of integrity will be there. Are you following integrity? Somebody else cannot modify. Why? What happens if somebody modify? Message is somebody modified. Then what happens?
S will also change.
S will change. So signature is changed. So we can check with the signature. That is one point. But in physical documents, even one letter you remove somehow, right? Signature is not, signature is there. It is a digital signature. Really, if you implement it, is far better than even physical signatures, right? You have a will. In that will, I will replace 10 by, or I do something. So, but original signature, mama ka, papa ka, kisi ka, older people ka to hai, right? In between, somebody will nicely change something, right? But here it is not possible. Yeah. So integrity will be there, and authentication is there. Authentication means who sent this message. That will be clear. It is because Bob only. Because this signature is verified by using public key. Na? Whose public key? Bob's public key. So that is so authentication is also known. It came from the Bob's only, right? The beauty. Other one is that non-repudiation. Now later Bob cannot deny. Yeah. It is because your public key, when I do it, signature is coming. It is verified. It is verified. So then Bob cannot deny later. Is it three parts are clear to you? Integrity, authentication, and non-repudiation. How powerful it is. This is what you understand. Kanak, is it clear to you?
Yes, sir.
Yeah, good. Okay. Suresh, is it okay?
Yes, sir.
Yeah, good. Okay. Now, so then what happens? Alice, when she receives, so she will use the public key of Bob's, right? And she will take X and S input verification algorithm, and it is true or false. Then verification will be done. Yeah. So I don't know. That is my problem now, but I will not take much time. So he may repeat it. Subhamoy Kundu. If he is using RSA digital signature, but I'm telling that this is the most simplest digital signature to explain. Okay, you will. That's why I'm going little fast here. So he may repeat it later. Yeah. So you know that how RSA encryption scheme I already explained. So Bob will take two big primes, right? P and Q, and computes n is equal to P into Q. Then E is the random. It is the public key. You see that what is advantage of E can be taken randomly? Can you say something? One application in terms of digital signature, somebody can comment. What is the advantage of choosing many E's? But of course, at one signature, we'll use one E only, right? I told actually answer. Yeah, but even then, can somebody help me? How many private keys I can construct? Hello? How many private keys I can construct? What is a private key here? Okay, in RSA crypto system, what happened? We'll take two big primes P and Q, and we'll compute P into Q, and we'll choose E. E is license between 1 to Pn, and GCD of E comma phi n equal to 1. And then with that allows us to compute D. It is inverse of, so D is unique now. Once E is chosen, then D is unique. Yeah. Okay. Now RSA keys are, it is key generation, right? So Bob's private key is D comma P comma Q. What is Bob's public key? N and E. So private key is not E, sorry. Private key is D. Yeah, sorry. Yeah. Any questions? Now, how many choices for private keys are there? That is E. How many choices are there? Public key, whatever. Yeah, public key. How many choices are there? Of course, E and D are same. Okay, don't worry about that because they are unique. They are inverse to each other, right? Yeah. Is it okay, or can you answer now? Okay. My question is that what is advantage of that choosing different Ds or different E's? Hello, am I audible?
Yes, sir, you're audible.
Okay, see, one person will see Bob and Alice, but now Bob and somebody else also may be there, right? So he also want to send a signed message, right? Then now Bob will change the public key. Sorry, public key and private key. Can he change the public key? Yes,
No.
right. No, he may change now. See, signature. See, again he is using the same public key, private key. Then many signatures, messages and signatures are coming. Now there is a small threat. So see, already public keys are known. Now I have many X and X, right? So there is a small problem. So what Bob will do now, for other person, he may use, but he will choose the same NPQ, same PQ, but he may use another E. E can be modified. Then only here these D and E will be modified. Remaining PQD, still it is very secure. Is it okay? What I'm saying is clear?
Yes, sir. Yes.
Yeah. So then I have a different signature scheme, different private key and public key, but still very nice. But some of the data fixed in both the cases. PQ and N are fixed, right? Yeah. Okay. Now coming back to this. Yeah. So basic RSA signature scheme, how it goes. So Bob will take the private key. You know that in the signature scheme, private key is used in the signing algorithm. Private key used in the signing algorithm because Bob only knows the private key. So public key is N comma R. What is R? Okay. Public key is N comma E. Okay. I don't know why I wrote E. Okay. So yeah, this is E. Yeah. Okay. Let me write one more time. So public key is N comma E, right? Yeah. Okay. What Bob will do? He will send N comma E to everyone. Public. Okay. Now he will also compute the signing algorithm. So X is the message. What is the signing algorithm here? You understand? You understand? This is the beauty. Now you understand the RSA cryptography, RSA digital signature. What is he is doing? Bob is doing. Somebody else will say. That's the reason only. I'm requesting you to say. You read it. Yeah.
Sir, I didn't understand your question. What did you ask?
I am asking that. Can you read this? Yes, that much only. Not a question.
Oh, x to the power d mod n.
Yeah, right. What is D?
So we had chosen E, and E was d was the inverse of E mod n.
Yeah, so D is the private key, right?
Yes.
Only Bob only knows. No one else will know, right? So Bob, what he's doing now, he took the message X. X is the message, right? Message he took, and then he do the secret key, and he done X power D mod n. So mod n is now public. E is public, right? What Bob will do, Bob will send a message and a signature, right? So now everyone get it. Now all people get N and E, and all people know X and S, right? Now anyone can verify it. Not only allies, right? Anybody else can verify it because everyone knows N, everyone knows E, everyone knows X, and everyone knows S. How allies will verify now? Allies or anybody, how will verify? So this is a signature came. So S power E will do mod N. Since E is known, N is known, S is known. So I'll compute S power E mod N. But where X is used now? Hello. What is S now? What is S? Do you remember?
X power d mod n.
X power D. Now X power D, now power E I am doing. Then what I am going to happen?
X, only X remains.
Only X remains, right? So X dash equal to X, then it is valid. Otherwise it is invalid. So it is only true or false. If this happens, it is true. If this happens, false. Right, I'm writing field actually, sorry. Yeah, false. Right, beautiful, correct? So very simple, right? D and E only we used both the sides. And D is the private key and E is the public key, publicly known. And all the things are used. N is used, E is used, X is used, S is used, right? So finally, X is used to check whether X dash equal to X or not. S is used to power E, right? Then we'll get X, right? So I think this is very clean RSA digital signature. Any questions?
No, sir, it's clear.
It's clear, right? Yeah. So any other person, one more person? Rutuja, is it clear to you? Are you there?
Yes, sir.
Yeah, it's clear. Okay, good. Okay, now I'm coming to the Ankita's thing, right? So I'll just give one example so that things will become easy. So let us take P equal to 3 and Q equal to 11. Actually, we'll take very big primes, okay? 33 and phi of n is equal to 20, you know that. So phi of 3 is 2 and phi of 11 is 10, so 20 will be there. And 3 comma 20 GCD is 1. So we'll compute to D. So 7, you can easily see 7 into 3 modulo 20 is 1, right? So then suppose X is the message X, right? Now what is the signature? Signature equal to 4 power 7, right? So we'll get 16. So what sent? Bob will send 4 comma 16. So how do you verify? So now 16 is reached, then we'll do power 3 equal to 3. So then we'll get 4 back. So it is, of course, 4 back or not S, then it will be done. Yeah. So now in between Eve there, right? Eve knows what? Eve knows S belong to Z and N comma E, X equal to S power E, right? So there are certain questions here. So is there any way that I can do another signature, another signature I will add? Okay, here I want to do something. I want to tell you something. Actually, till now I told that signature scheme pay, I will take M, message M, and I will use the private key and I will get the signature, yes, right? But actually, people will use the, instead of M, they will use the hash function. Are you following? They will not apply signature algorithm directly on M. They will apply on hash function of M. So both the parties know hash function. Both the parties knows the hash function. Who? Bob and Alice or whoever. Or otherwise, you can say that hash function is also made public. Is it okay, Kanak?
Yes, sir.
Yeah, what is hash function? Hash function I told you in the previous class, but I'll repeat. Hash function take any size. You remember that Kanak told some star, right? How do you pronounce? I know. Knee operation, right? Knee operation, right? So there you can take alphabet and you can create messages of any length. But now like that it will take, but it will take arbitrary length, finite fixed length, right? Yeah. So hash function main duty is that it convert. So messages are going to be any length, but hash function convert them to fixed length, right? Okay. So then what is going to happen? There is a possibility that two messages M1 and M2 can apply hash on them, right? So they may be equal, right? Alice may, Eve may use that technique. Yeah. So, but actually these are also infeasible. That anyhow Kaustav will tell. Is the Kaustav is here?
Yes, sir.
Yeah. So Kaustav will tell later regarding hash function. So actually digital signature will use hash. Okay. So there is a possibility that if you are not using proper hash, then there is a possibility that integrity will be lost. So she will send other signature and the signature is verified, and she will replace both X as well as S, right? Some problems will come. Okay. But I will not go into details. It will now give the flow of this, what I'm talking, right? Yeah. Yeah. Now I'm going to Elgamal signature scheme. So here, so this is Ankita told, but I'm repeating once little faster way. Choose a large prime P. Choose the primitive element alpha, or yeah, or in fact, some people take a primitive element for a subgroup of ZP star. That is actually one more algorithm is there, digital signature algorithm. Maybe one of them they may tell, I don't know. Otherwise, I will tell later. So DSA, it is called simply DSA. Actually, digital bad luck is that digital signature name is used actually for another algorithm like Elgamal. So people modified Elgamal crypto signature scheme and they created new signature algorithm that is called digital signature algorithm. There they will use the subgroup of ZP star instead of original group ZP. Now people are using digital signature algorithm for digital signatures. Yeah, okay. Yeah, that is another interesting algorithm. So I think it is in the syllabus also, it seems. Yeah, okay. But so if you understand one or two algorithm, you will understand everything slowly. Yeah. Choose a large prime P and element. Choose a random integer D. Now this is the place again. See, I can choose different Ds for, but one particular person I will choose one message I will choose single D. I am telling, and I hope it is clear to you. For one message, I will use one D only, but you are sending some other signature pair to somebody else, then I will choose another random integer. That's the advantage of having these random integers in the algorithm itself. Okay. Anyhow, so it is actually key generation only. This is we already discussed. So now we'll take a D belong to 2 to P minus 2 and we'll compute alpha power D. Alpha is the generator and we'll compute beta. Now what is the public key now? P, that prime P, alpha generator and beta. What is the private? That D, the random integer. Yeah. So Elgamal signature generation now, right? Choose a random KE belong to 0, 1 to up to P minus 2. So now this is sorry, I want to say this is the thing help us to prepare different digital signatures. Yeah. So GCD of KE comma P minus 1 equal to 1. So compute the signature parameters. What are these things? So KE inverse we will do, but of course don't worry that Ankita told KE inverse here, so we can use at any place. This R and S computed. What is R? alpha power ke. What is alpha? Generator. And then what is X? Message. What is D? D is the private key, right? D is the private, right? D is the private key. What is D? D is we choose randomly and we compute it, right? Yeah. So now here D is used. Now this R is used here and K inverse is used here. So this entire thing is now signature. Signature is a tuple now. Now earlier X comma S, now this is entire R comma S become S now. Is it okay? And also here we are not using the private key. Only in S we are using the private key. R is used now again in S. So basically S is the main thing. Is it okay? Am I fast or something? Kanak, are you okay?
Yes, sir, it's clear.
It's clear, okay. Okay, now these are the things, okay. Now Elgamal signature verification, right? This is what I'm telling her that what is that LIS knows or any person knows. Now they know X, they know R, they know S. They also know public P, alpha, beta, right? All of these are known. Now we need to define verification algorithm by using these, right? Okay, how do you do that? Okay, so verification algorithm. So LIS have now, see, that's what I wrote, P, alpha, beta, X, R, comma, S is pair, right? Now you pair, you cannot interchange. I cannot separate R, comma, S, right? Pair is very important because in S computation, R is used. So it has to go that pair only. Yeah. So compute the value T equal to beta power R and R power S. Is it possible to compute this? Because beta is known, R is known, S is known. See, what is the T is T value? Beta power R and R power S. And everything is known publicly, right? And mod P also known. We'll do all these things. Now, when it is verified, when T equal to alpha power S, alpha is known, yes. S is known, yes. Then T equal to alpha power S, then it is valid, otherwise not valid. But why this is the thing, right? This is what I asked her. You remember? Okay. Any questions till now? Yeah, you are now mysterious why this is actually, right? You may be mysterious that why this is T equal to alpha power S. That I'll explain now. Is it anything, any doubts?
No, sir.
No doubts. Very good. Nice. Now coming here. Okay. So beta power R and alpha power S. Okay. What is beta? You remember beta we computed earlier? Beta equal to alpha power D. It is D is very difficult to compute from alpha power D because of D is
Discrete log.
discrete logarithm problem, right? So in fact, see, Elgamal version of elliptic curve crypto system is also there. Somebody can take up that. In fact, Ankita will take up this. It will be better. You can talk to her and again.
Sir, Amaya and I are doing that.
Are doing?
Yes,
We are
sir.
doing it. Yeah, good. Very nice then. Yeah. Okay, good. No. You are doing that encryption and all, but signature also are doing signature scheme.
No, sir, not so much.
That's what I'm telling. Elgamal digital signature,
Oh.
but by using the elliptic curve cryptography, right? Yeah. Because see, signature schemes, digital signatures are derived from what? For the digital signatures, what is it we need? We need a public crypto system, right? Yeah. Okay. Anyhow, now coming to this, beta power R and R power S. Beta equal to alpha power D power R. And what is R, right? R value is not, KE not known, okay. KE not known to the public. But even then we can do, that is a beauty. That's why the K inverse is brought here. Otherwise it is difficult actually. It is actually very, very, very powerful brain used actually. Digital signatures are not that easy. Okay, the verification algorithm, how do you verify? So this KE is random, right? Choose a random KE, but it is not affecting even without revealing that KE. Okay, let us see. Now this alpha power KE, that is R my R power S, right? Now this dr plus KES, okay, dr plus KES. You see that here from this you can observe that I can multiply both sides with K inverse. Can you say something from here? What is X equal to? What is X? X equal to KES plus dr, correct? Modulo P minus 1. Are you able to understand that? Yeah, not complicated, right?
Yes.
Yeah. So that is exactly, see, this is actually alpha power R into, this is actually alpha power S X actually. This is alpha power X. Yeah. Okay, so now this X and this, these are both are X now. So that's verified. Yeah. So this is a thing I put question mark, but I explained you. This comes from here. So signature is verified. Yeah. So I'll give one example that I will stop today. Huh? So, but before that, any questions you want to ask me? Okay, good. So very interesting actually, very nice topics. Yeah. So now one example is that Bob uses a prime 29 and the primitive root alpha 2 is the primitive root generator and D equal to 12. And 12 is actually what? It is relatively prime to P minus 2 or some P minus 1. How we choose D? Oh no, D is anything, right? D is anything, alpha power D we will do. D equal to 12. Yeah, D you can choose. It is key generation only. Yeah. So beta equal to alpha power D, 2 power 12, 7. Okay, now what is public? P is public, alpha is public, D is public, beta is public, but D is private. Yeah. Now signature scheme. So X is equal to 26. Now K is equal to 5. So 5 comma 28. Why I took 28 here? Yeah, 28 is because here 29. Prime is 29. So I took 5 comma 28 GCD is 1, right? So how many choices are there for 5 now? KE. These are my exam problems, if I may ask, but I'm now revealing to you. How many choices for KE? Phi of 28. Why this is useful? That many signatures I can make each randomly. So for one signature scheme, I will use one KE, right? But I can choose any KE, right? It is random. Yeah. So that is the beauty of this. Yeah? Okay. So R equal to alpha power KE. Alpha is 2. 5 is my randomly chosen number. So I'll get 3. R equal to 3. Now S will compute. X minus dr into x e power inverse. So we'll get some 26. Okay. Now what is that? We'll send message and here somehow it is accidental that S and message are same. So 3 comma 26 pair will be sent. Now verification. So they will verify it. Yeah. So this is the thing. So yeah. Any questions?